Hi, my name is Stewart Lynch, and in this video we're going to take a look at threading and Grand Central Dispatch in Swift. We'll investigate what threads and queues are, as well as the Grand Central Dispatch, or GCD, the API for managing your queues. In the process, we'll also touch on synchronous versus asynchronous code, and finish off with an overview of DispatchGroups. If this is something you want to learn, then keep watching. Before I jump into the code, I think it's best that we first get a better understanding of the beast. Most modern operating systems let you specify a thread of execution to use. Every iOS application has a main thread, which is there to display your user interface and listen for events. Complex computations may slow down the main thread and freeze the app. And here's where multi-threading comes into play. We must move all of the heavy lifting to a background thread, and then move the result back onto the main thread. These threads might be executing their code simultaneously with a multi-core iOS device, but they might also just be switching back and forth really quickly, and some threads get a higher priority than others. A queue is just a bunch of code blocks, lined up or queued up, waiting for a thread to execute them. Note, you don't need to worry about threads in Swift, only queues. The system takes care of providing and allocating threads to execute code off the queues. GCD stands for Grand Central Dispatch, and this is the API for managing your queues. And its main responsibilities are creating a queue and putting blocks of code on a queue. Blocks of code waiting in a queue are held in a closure, and we'll look at that shortly. But first, let's look at the different kinds of queues. There are two different types. The main queue is the most important one of all. It's the queue where all blocks of code that affect the UI must be run on. The system uses a single thread to process all of the blocks of code from the main queue. Background queues are used to queue up any long-lived non-UI tasks. These queues are often running simultaneously and in parallel with the main UI queue, and you as a developer can determine which of the background queues get more priority over other ones. And you do this by specifying a quality of service, or QoS, and we'll review that shortly. To create a queue, you use the DispatchQ struct and one of its static functions. To create a queue on the main thread, we use the static function main. To create a background queue, you use the static function global, and you can specify one of 4 different quality of services or priorities. These two are qualities of service that you apply when a user needs the task to complete promptly. UserInitiated Tasks have the highest priority of the system. And use this class for tasks or queues that interact with the user or actively update your app's user interface. For example, use this class for animations or for tracking events interactively. User-initiated tasks are second only to user-interactive tasks in their priority on the system. You assign this class to tasks that provide immediate results for something the user is doing, or that would prevent the user from using your app. For example, you might use this quality of service class to load the content of an email that you want to display to the user. The next two types are lower in priority for execution. Utility tasks have a lower priority than user-initiated and user-interactive tasks, but a higher priority than background tasks. You assign this quality of service class to tasks that do not prevent the user from continuing to use your app. For example, you might assign this class to long-running tasks whose progress the user doesn't have to follow actively. Background tasks have the lowest priority of all tasks. You assign this class to tasks or dispatch queues that you use to perform work while your app is running in the background, like maintenance tasks or cleanup. So the 4 priorities are listed here in the order of priority. If you don't specify a QoS, it will be assigned the default case, which is between user-interactive and utility. There are 2 ways that you can add code to your queue, either synchronously or asynchronously. When a work item is executed synchronously with the sync method, the program waits until the execution finishes before the method returns. That is, before the next line of code following the code block gets executed. This means that it'll block the user from doing anything until the code is completed. The code block is executed as the closure on either the main or background queue, like this. When a work item is executed asynchronously, the async method, the method call returns immediately. And the execution of the closure is done the same way as above, we just use async instead of sync. Both synchronous and asynchronous executions can be done on the main or background threads. But the fact of the matter is you almost never use a synchronous execution, so we'll focus on asynchronous. But enough of the theory, and let's take a look at it in practice. Let's create a new playground and type in some code. In our last two slides, we talked about how with dispatch queues you can execute your code synchronously or asynchronously. With synchronous execution, the queue waits for the work, and with asynchronous execution, the code returns immediately without waiting for the task to complete. Let's create a global queue with a synchronous execution inside the closure. We'll sleep for 2 seconds to simulate some lengthy process, and then print a statement. We'll follow that outside the closure with another print statement, so print outside. When we run this, it takes a while for our print statements to show up. It waits 2 seconds, prints the first statement, and then carries on after the closure has completed. The sync code is blocking the execution of that second statement until after the closure has completed. Let's change sync to async and update our print statements. When we run, we get the second statement executed immediately, and then 2 seconds later, we see the first statement. The async execution is not blocking our program from proceeding. There's one more async execution to consider if you want to delay the start of the code. We can use Async After, and it can be executed on any queue, but typically on the main queue. With Async After, you can delay the start by specifying a deadline and entering dispatchtime.now and then adding a number of seconds. This can be shortened like this, and it's quite readable. We just enter .now plus 2. So with this code, the first block will execute after 5 seconds and immediately goes on to the next block, which only waits 2 seconds. So running the code, we get that second print statement after 2 seconds, and that second block will have waited 2 seconds already, so it only has 3 seconds more to get executed. This is more complicated than you may think. You'll not be calling dispatchqueue.global very often on your own, and the reason is because a lot of asynchronous iOS APIs do the tasks automatically on a background queue, sometimes unbeknownst to you. So let's take a look at another example. For this, I've created a starter project in SwiftUI, and you can download it from the link in the notes below. Let's take a look at the code. When the app launches, the content view is presented. It contains a space to display an image followed by 2 buttons. The first button will call code that will retrieve a dog image and will update the state to refresh the screen with that image once it's been retrieved. The second button simply toggles a state variable that will cause the screen's background to alternate between green and white based on that Boolean state value. I'm using the MVVM architecture here to keep our code separate, and in the dog view model, there is our published image that when changed will update the observed object in the content view, causing the image to be displayed. Now I want to be clear here that this is not normally how I would structure this piece of code. This is simply a way that I can demonstrate this concept of threading and GCD. The getDog function sets the image to nil, no image, then transforms the string into a URL and grabs the content of the URL, which happens to be a JSON object. We use JSON decodable to decode the object into a dog instance, and all I'm concerned with is the image URL. Once we have the image URL, we can make a call to this URL, extracting the image data. Then, to simulate a slow connection, I'll sleep 2 seconds before converting the data to a UI image and assigning it to the image variable, which will then update our UI on our content view. Let's see how it works. When I run it, I see that I can toggle the background color at will. But when I execute the fetch for the image, our UI is blocked. Even though I'm tapping on the Change Background button, the change doesn't happen until after the image has been retrieved and the 2-second sleep has completed. The reason is that, by default, our code is synchronous. So it waits for however long it is going to take to fetch the JSON data and the image and the 2-second sleep before going on to setting the image. We can fix this then by putting all of the code above this in an asynchronous background queue. Before we do that, however, I'm going to insert some print statements so that you can see what's going on. To assist, I have a couple of static utility functions. The location function takes one parameter, which is the name of the file that is executing the code, and prints out the location and calling function. The second queue function calls an extension on DispatchQueue that accepts whatever string I want to give it and then prints out the action string followed by the type of queue you are on and the thread. So back in our function, we'll call that log.location function, passing in the special literal for the file. Just before we get our JSON, let's log the queue information. Similarly, just before we get the image, let's log the queue information there too. And finally, let's log when we upgrade our UI. Let's bring up our bottom panel and see what gets logged when we run our app and fetch an image. We see that we are in the dog view model file running the getDog function at line 15. And each of our 3 queue logs, I see that we are on the main queue and thread. So now let's finish our blocking problem. What I'm going to do is place all of our execution code in a background queue. I'm going to use DispatchQueue.global with a .UserInteractive quality of service and execute this asynchronously. Let's run it. I can tap the getDog image button, and while it's fetching the image, change the background. That's great, but not so fast. The app hasn't crashed, but I do get this notification that publishing changes from background threads is not allowed. If we do not fix this, there is no guarantee that our app will perform consistently. We also see the offending line of code is highlighted with a purple notice telling us that this must be on the main thread. Well, we know how to do this. We'll surround this code with another dispatch queue, but this time .main, and do it asynchronously as well. This time, as before, we can change the background as the image is getting fetched, and there are no warnings once the image has been retrieved. Our log shows that indeed, the fetching of the JSON and the image were done on the UserInteractive background thread, and the updating of the UI is done on the main thread, as it must. Now, everything comes at a cost, and so does this simple approach. There's a reason people tend to use another method for network requests, which are not just for JSON strings and images. Swift lets you observe the progress of the network operation in real time if you choose to use URL session and its delegates. This comes in handy for larger network requests where you can let the user know about the progress with fancy progress views or something else. For simple image loading, our easy approach will do more than good. However, for sophisticated tasks, you better be looking at this different method. So instead of using our own code as we have done here, you'd normally use either URL session or something like AlamoFire to fetch data like images from an external source. First, let's create a new function called getDogWithSession, and I'll paste in the first 4 lines of code from above. We'll also create another variable called session that is a shared instance of URL session. We'll first check to make sure that the URL is valid. Next, we'll call the session data task function, passing in the URL, and it has a completion handler that when the task is completed provides the data, a URL response, and a possible error. We're just going to ignore the response. But let's log that we are processing the fetching of this JSON. Now, if an error has been returned, we'll crash with a fatal error. After that, we'll do exactly the same as we did above within our background queue. The final thing we have to do is ensure that we do have a task resume, or else our code won't be executed. Back in Content View, let's make sure we call this function instead of getDog. Testing this, we see that it runs just as well as the getDog function did. In our console, we see that even though we did not do a dispatch queue onto a background thread, we actually are. And its quality of service is unspecified, but I don't really care. It just works. The URL session handled the placing of our code onto a background thread. And of course, the UI is updated on the main thread because we left it at that. There's one final topic I want to cover, and that's dispatch groups. Groups allow you to aggregate a set of tasks and synchronize behaviors on the group. And you can attach multiple work items to a group and schedule them for asynchronous execution on the same queue or different queues. When all work items finish executing, the group executes its completion handler. You can also wait synchronously for all tasks in the group to finish executing. And the purpose of dispatch groups is to let you know when several independent tasks have completed. So let's return to our playground, and I'll comment out the previous code, and I'm going to create a global dispatch queue in a dispatch group. So let queue equals dispatch queue.global, and let group equal dispatch group. Now there's 2 different ways, as I mentioned, to implement this, and each way gives a different result. In this first example, we'll take a look at the synchronous waiting. Here's how we can wait for 2 tasks to complete. We'll add a group parameter to our async execution. I'll sleep for 3 seconds and then print task 1 is done. Let me just copy that code and paste that, and I'll change it to sleep for 1 second and print task 2 is done. Now I'm going to follow that with a group.wait, and this specifies that everything must wait until all of our group tasks are completed before carrying on. Once completed, I can print that all the tasks are done, and we can continue execution. When I run, because our 2 tasks are asynchronous, we see the print from task 2 first because there is only 1 second of sleep. Then 2 seconds later, task 1 is done. Then, only after both have been completed, we get the final 2 print statements. The second way for working with dispatch queues is by balancing the calls to enter and leave. We indicate the start and end of an async operation. And this is especially useful when working with code that you cannot change, for example, system or third-party frameworks. We can keep the same queue and group, but let's comment out the code. We'll start by entering the group with group.enter. Now we can execute our async closure with the group parameter as before, but at the end of the closure, we'll leave the group with a group.leave. As above, let's repeat this with a shorter sleep time. Now we can get notified when the group's queues are completed and execute some code. And we'll use the group.notify function with the queue as an argument. Outside of this notification, let's print continue execution. Now, when we run this, we get the continuous execution printed immediately because the notify function is not blocking our code. It's asynchronous. This is then followed by the second asynchronous task because it had the least amount of time to wait, and then the first task before finally printing all tasks are done. So I hope this has given you a better understanding of threads and the synchronous and asynchronous nature of dispatch queues. I have lots of other videos available and in the queue as well, so please check out the rest of my channel. You can also visit my website to see the apps that I have available on the App Store, and visit my GitHub page to see what I have available as public repositories. If you like what you've seen, give it a thumbs up and subscribe to my channel. And ring the bell to get notified when I post new videos. I'm most active on Twitter, so please follow me there as well to find out what else I'm up to. Thanks for watching.